APGC. Oh. All right, okay, so we're being recorded, so if you do not want your gorgeous face to be recorded for posterity on the associated video, turn your camera off now. Or if you do want your face later on when you're asking questions, turn your camera back on. So today we've got a friend of mine speaking, to be brutally honest, Debbie Rees, and she's going to be the first seminar of 2023. I nearly said 2022 there, of the APGC. Debbie and I have been chatting an awful lot lately about crop storage. They've got a long history in crop storage, and of course we are now building crop storage facilities here at the James Hutton Institute. So the links between NRI, where Debbie's based, and us will be very, very stronger over the next several years, and hopefully progressing beyond when both Debbie and I are long gone, one would hope. That'll be for a wee while yet. Anyway, so today Debbie's going to talk to us about listening to the fruit and vegetables. Her background is in plant pathology. She's had an illustrious career working in that in the UK and overseas, so working in places like Sub-Saharan Africa and Latin America. And at the minute, she's lead scientist at the Produce Quality Centre down at NRI. And their main target is looking to basically optimise handling and storage of fresh produce. So their links with industry are very, very strong. So much like JHI, they're involved in fundamental science and translating that through to industry. So you don't want to hear me, you want to hear Debbie. So I'm going to pass it over to you, Debbie, to give us your talk.
Okay, thank you very much for the introduction, Derek. I'm going to try and share screens. Let's see if we can get this to work. I think it's that one. So bear with me. Okay, so I'm hoping that you are now seeing my first slide, which is a picture of lots of fruit and vegetables with little happy faces on them. Okay, so as Derek said, I'm going to talk about listening to fruit and vegetables to improve storage and reduce waste. So I come from a background of doing research, and I start off with a bit of a plug that research and development of technologies for supply chains is really important for the fresh produce industry. We are at a bit of a critical position in the UK at the moment in terms of what research facilities and expertise is available for UK horticulture and agriculture, which is something that Derek and I have talked about a lot. Anyway, in this talk, what I'm going to do is introduce one approach that we've been using that can be applied to several types of produce to try and improve storage and handling. So just to introduce myself, as Derek said, I work for the University of Greenwich, the Natural Resources Institute. I'm based down in Kent. We have a facility there for doing storage research, actually based on the East Morling Trust site, neighbouring with NIAB EMR. We are now the largest fresh produce storage research facility in the UK after the closure of Sutton Bridge in Lincolnshire. We tend to focus on controlling atmospheres. We have 10 temperature controlled rooms. We have more than 70 chambers where we can independently control the atmosphere. Okay, I'm seeing if I can move on. Okay, like that. Okay, so this, for example, is some of the equipment that we have that's actually been there for several decades for controlling atmosphere and trying out different storage protocols. Moving on, more recent equipment that I'm actually going to introduce you to in this talk, like the previous slide, these are chambers, each one of which we can control the atmosphere in and test out different storage protocols, and another slightly smaller iteration of that same equipment. But let me explain the background of this. So basically, if we are trying to store fruit and vegetables, our aim is always to slow metabolism so that we can have the produce living for longer, preserved for longer. when I teach students about storing fruit and vegetables, I always emphasize that what we have is a living organism, and that our aim is to keep it happy and healthy and stress-free. Okay, one way we can monitor how produce is behaving is by looking at respiration. So it's always breathing after it's been harvested, and that breathing, that respiration, is necessary to provide the energy to keep the tissues healthy. So here's a picture of an apple. It's taking in oxygen, it's breathing, producing CO2, water, and heat, in fact. So the advantage of being able to monitor that respiration is that allows us to optimize storage conditions. And generally, if we want good storage, we want to have slower respiration, as I said before. But there comes a point in anything that we do that if we take the conditions too far, that we start to stress the produce. So in this case here, we have a graph showing you the respiration rate of produce as we take the temperature down from ambient down to lower and lower temperatures. And for all produce, there will become a point where that temperature is too low and the produce starts to be stressed. And often what we will see is that respiration then starts to rise. As well as being able to control temperature, we can control atmosphere. So another way to slow down the metabolism, the respiration, is to reduce the oxygen from, in this case, air. The concentration of oxygen in air is 21%. If we take the oxygen down, there comes a point where the respiration starts to drop. But again, if we take it too low, we'll get stress and the respiration rate will increase. We can do the same with carbon dioxide. So some produce is particularly good at slowing down its respiration if we take the CO2 high. So CO2 in air is 0.04% rising, but never mind. And if we increase that CO2 concentration, we slow down respiration. But again, if we get to a point where it starts to be stressed, you'll see that respiration going up. So within reason, if we can get that minimum respiration rate, yeah, that's good. I mean, of course, that's a vast oversimplification, but within reason, that is a good way to go. So controlled atmosphere storage is commercially very important. Here we have pictures of apple storage in Kent. So where I come from, Kent is the fruit bowl of the UK, and we're in the centre of the apple growing industry. So if you wander around Kent, you will find a number of controlled atmosphere stores sitting in the middle of fields or wherever they might be, some in quite large complexes. So basically, I got that in the wrong order. Let's go to the next one. Yes, I wanted to show you this. The importance of CA storage is that it can take apple storage from just a few weeks or possibly 2 or 3 months up to, in some cases, almost a year. So basically, if we take something like Braeburn or Gala, if we just store them at low temperature, we can store them for 2 or 3 months. But if we take them into controlled atmosphere, we can go up to several months. But there is a move to try and extend that further and further. And the concept being that if we can take the oxygen concentration lower, as low as we can get, we would be able to get that CA storage even longer. In order to try and do this, we were part of a project that was funded by the Agritech Catalyst Mechanism, Innovate UK and the research councils, called SafePod, which was to develop a new technology to allow intelligent control of fresh produce storage by monitoring the respiration in storage. So this project was, as Derek says, we worked with a number of UK companies. So Gotham's, the apple producer, Avalon and Sainsbury's. But key to this was an engineering company, Storage Control Systems, which has a branch both in the UK and in the US. So what were we trying to do? So this is this graph shows you basically what happens to respiration over a range of oxygen concentrations. We can measure respiration in two ways. We can either measure it by oxygen uptake, because respiration uses oxygen, or we can measure respiration in terms of CO2 evolution. So here, this graph shows that as we reduce the oxygen concentration from 21% in air, if you followed oxygen uptake, you see that there comes a point where the respiration rate drops quite dramatically. If you look at the CO2 evolution, you see the same. But there comes a point where the oxygen concentration is so low that the apples can no longer get enough energy from respiration using that oxygen. And so they switch to anaerobic respiration, in which case they use less oxygen, but they produce a lot of CO2. So at that point, you'll see suddenly the CO2 evolution increases. Below this point, then, the fruit will go anaerobic. And that's what we don't want. So at below that point, the apples would start producing ethanol and the tissues would be damaged and stressed. So basically, if we can measure both the oxygen consumption and the CO2 evolution, and we look at the ratio of those two measurements, then we find that at the point when the apples go anaerobic, that ratio suddenly changes. So we measure something called the respiratory quotient, the RQ, and that ratio suddenly increases from somewhere it would be close to 1 under normal conditions, and it suddenly increases. So this was the technical basis of how we decided to check what was happening to those apples during storage and try and hit this low oxygen point that would give us the longest storage potential. Okay, so this graph basically, this table basically shows, as well as what I said before about the CA being able to extend storage, one of the things it highlights is the difference between different apple varieties. So you might think an apple's an apple, but some of these apples you can store at high CO2, some you can't. I'm not going to go into the details of why that is the case at the moment, but it's very notable that different apple varieties can cope with very different controlled atmosphere conditions. We also find that not only do different varieties react differently, but the apples respond differently in different years. So depending on the growing conditions, the optimum storage environment can be very different. Which means that if we are trying to hit that point, that critical point where we get the absolutely lowest respiration rate, we have to be able to monitor what's happening to that fruit each year. Otherwise, we might go into that anaerobic area. So basically, what this project did was it designed a respiration chamber. And here is a picture of that respiration chamber, able to hold 70 to 80 kilograms of fruit. And it was designed to be able to go into a commercial apple store. So the picture on the right here is actually one of these respiration chambers, which was called the SafePod, sitting within an apple pallet bin and placed at the top of a commercial store. The picture here, and I'm guessing you can see my cursor, is the same but in a US Apple store. So in that case, in this particular case, they're controlling CO2 by putting soda lime there. So American, UK. Okay, so what are we actually doing? So here is my picture of the SafePod, just a diagram. What you didn't know, what I didn't tell you, was that there is a valve at the bottom of that chamber which can be open or closed, so that we can either have that chamber sharing the surrounding atmosphere, in this case a commercial CA store, so in this case lowish oxygen and, depending on the variety, an increased CO2 concentration. Or we can seal that chamber, close that valve, so that the any change in the atmosphere within that chamber is due to the respiration of the fruit. So what do we see in practice? So this graph on the right is showing the oxygen concentration and the CO2 concentration within a CA store. And the first part, this is under CA controlled, and it's following what's happening in that store. And the control system is keeping them relatively stable. At this point, the valves were closed so that the oxygen drops and the CO2 rises. And we can use those changes to measure, to calculate the respiration rate of the apples. So in practice, what we're seeing, as the oxygen decreases within that chamber, we're seeing the respiration rate as measured by oxygen going down. The respiration rate as measured by CO2 starts to go down and then starts to increase. And so we can calculate that respiratory quotient that I mentioned. And in this case, what we're seeing is that the respiratory quotient starts to rise at oxygen concentrations below 0.6% oxygen. So quite low, and this is lower than growers ever had the confidence to store their apples at before. So that in this case, with this data, we're saying that in that apple store, although it started off with about 1% oxygen, we could actually take that oxygen down to 0.6 before we had any problems with those apples. So the concept was that at intervals during storage, most of the time this chamber would be open, but at intervals it would be closed to do these measurements and then calculate what oxygen concentration we could put in that store. So as well as working out what the optimum oxygen concentration is there anything else that we can do from the respiration measurements that we're making? And actually, by chance, lucky for us, but unlucky for the apple growers, in the second year of this project, there was actually a major problem with the Gala apples in Kent. And many consignments, complete consignments were lost because the apples started to develop this senescent breakdown. It's heartbreaking for growers when this happens. To lose a store of maybe worth 30,000, 40,000 pounds or more. And if you've got this sort of problem, like in 10% of your fruit, basically it's very difficult to sell it to supermarkets. So what we actually found was that if we had known, we could have predicted which of the stores were going to have this problem. Because what we could see was that the stores that had this problem started to develop higher respiration rates. And actually in advance of that problem becoming commercially important. So in practice now, what's happening? This system is being used commercially in the US and in the UK. Actually, it's taken off more in the US than it has in the UK, which is probably to do with the size of the apple growers. So wherever there are SafePods within stores, the respiration rate throughout the season is being monitored. The Storage Control Systems Inc. in the US is following those respiration rates and is providing a system online where the growers can actually check what the respiration rate of their fruit is compared to the industry average. So what this graph is showing, the green line here is the industry average of that year. So this was last year. I think this is Gala. And it's showing two individual stores. The one in red, significantly higher than that average. The one in blue looks good. So the recommendation would be that the red store here should be opened and the fruit sold. And in practice, that's what's being used more than the optimization of the oxygen concentration. So in practice, this is now becoming a very useful tool for the large apple growers to decide which of their stores they will sell first. So now it's estimated that over $325 million worth of fruit is stored with the SafePod technology worldwide. So that's including North America, South America, UK. And it's being used mainly to rank stores. One thing you may have noticed is that in the UK, Gala apples are very popular. It used to be that from April, May onwards, all Gala that you got in the shops was from the Southern Hemisphere. What this technology and similar technologies have done is they've allowed Gala in the UK to be stored at lower oxygen and to be kept for longer. And now what we're finding is that you can get Gala in UK Gala in UK supermarkets through to July and sometimes even August. So there is a measurable effect of this type of technology. Okay, so so far I've just been talking about apples, but one of the consequences of the technology that was developed for going into commercial stores was that it also allowed us to develop technology that could be used for doing lab-based trials of controlled atmospheres. So here we have, we call it, so the iteration that goes in the commercial stores is called the SafePod because it keeps the apples safe. And we then have the lab pod, which we can use in laboratories. And it's being used in a whole range of different sizes. So below we have the size which holds 60 to 70 to 80 kilograms of fruit, above the one that holds about 10. What's valuable about this compared to the technology that we used to use is not only can we control the atmosphere within these chambers, but we can also monitor the respiration. So we can use it to much more quickly determine the optimum storage conditions. So what are we using that for? This technology is now still being used to improve the CA protocols for top fruit. But it's being moved on to other things. So, for example, last year we started a project looking at improving controlled or modified atmosphere storage of cherries. Potentially, this could have a massive impact because the UK cherry season is only 6, possibly 8 weeks long. Cherries can be stored for 2 months relatively easily. So if we can do that safely and with good quality fruit, we could basically double the cherry season in the UK. We don't have to just stick with fruit. Here are 2 vegetables which store very well under CA, leeks and Brussels sprouts. So we've been doing trials with them as well. And something that we find enormous fun actually is that we're starting to look at doing controlled atmosphere storage of bouquets of flowers. And the reason that this is useful is sort of highlighted by that graph at the bottom, which shows the sales of flowers through the year. And you'll see that there are sort of huge peaks in sales. We all decide that we want to give our mothers flowers on Mother's Day. We all decide that we want to have flowers at Christmas and Valentine's Day. So the poor flower marketing people have to cope with the fact that they just do not have a flat demand through the year. They have to cope with this. So they say if they could keep their bouquets for 2 weeks, they could smooth over the amount of work that had to be done to put those bouquets together. So yeah, one more. We can also use this sort of technology for looking at the effect of atmospheres within retail packs. So one thing we've been looking at is slowing down the softening of pears once they have been packed. So again, the capability of being able to both control that atmosphere and measure the respiration is hugely helpful. Close to my heart, though, is that if we can improve controlled atmosphere storage, there are many commodities where we should be able to either prevent the use of air freight completely, or at least move some of the air freight over to sea freight. Even flowers from Africa are being tested in terms of sea freight rather than air freight. And we've also looked at asparagus coming from South America. So it's perfectly feasible, not in all cases, but in most. Okay, so now I'm going to move on to a different commodity, potatoes. So potatoes are stored long term, not currently under controlled atmosphere, but under air. The potato storers have a number of challenges. They have to prevent sprouting, and yet the most effective sprout suppressant, chlorprotham, CIPC, which has been used as the main sprout suppressant in the UK for over 50 years, the approval for this sprout suppressant has been removed. There are alternative sprout suppressants, such as the use of ethylene or mint oil, but they're not as effective as CIPC. So challenge for the potato industry. Another challenge for the potato industry is that is changes in quality during storage. So generally we have to avoid sweetening of potatoes because when they're processed, we may get acrylamide formation, which is a health risk. So in order to prevent sweetening, first of all, we have to avoid low temperature storage, as in down like 4 or 5 degrees, because we get low temperature sweetening due to the effect on metabolism. But we also find that for many varieties, they start to get what we call senescent sweetening after several months of storage. So, we have a few pictures of storage in the UK. So we have potato storage in boxes or in bulk storage. Okay, so the question was, could we, by looking at respiration characteristics, actually predict sprouting and predict quality deterioration? Could we use the tuber response to storage conditions to optimize storage protocols as we can with fruit? So storage control systems designed an iteration of the lab pod specifically for potatoes. Here, what was important was not only to get the atmosphere that was in the store, but also to simulate the same airflow patterns as you get in potato stores. So there was a lot of emphasis on getting horizontal airflow. So here we have Peapod for the potato pod, Mark 1, with airflow going that way. We decided this was too easily damaged, so then that became redesigned for this slightly snazzier looking version, the Peapod Mark 2. And the first question was, could we use the Peapod to see how the potatoes were actually responding to the storage conditions in stores? I show this. This is not a UK store, so please don't worry about the health and safety implications. We do not believe that this is a safe thing to do, so do not do this yourselves. But here is the Peapod sitting at the top of this American bulk store. You can't see them, but there are valves in the base so that this chamber here can share the atmosphere with the potatoes there. Now, there are all sorts of reasons why this is suboptimal. But we actually learnt a lot about potato response to storage conditions from this trial. And from the first trial in the UK, where we looked at box storage, where that Peapod went in a box at the top of a store. So concept similar to what we did with the SafePod for apples was that at regular intervals, the pod was closed so that it was isolated away from the storage atmosphere, and we could measure the respiration rates. We actually learnt a lot about what happens to carbon dioxide concentrations within potato stores and how the potatoes react. You may not think a potato is exciting, but actually metabolically, it's a lot more exciting than an apple. So the response, the way that the potatoes responded to their storage atmosphere was actually surprisingly large, a surprising level of reaction to changes in CO2, for example. And we also discovered that within storage trials, the response of tubers to what was going on in other stores in the storage environment. From early trials that we did at Sutton Bridge, you'd be surprised how much the potatoes responded. So watch this space. This is something that we're working with James Hutton and ADAS as well. Oh yes, I forgot to say, we can also watch the potatoes. And again, you may not think that it's very exciting, but you can actually watch them sprouting, which was useful. So I put in this slide as a bit of a plug, because what we would like to do is to use what we have learned from the development of the Peapod to develop the equivalent of the lab pod for apples. So to develop a system where we can actually do storage trials within chambers, where we can monitor what's happening within that chamber. For reasons of making this acceptable to the potato industry, we're looking at a system which is bigger than the lab pod. So we're calling it now the Peapod Maxi. But it would have capability of controlling the airflow so that we can simulate commercial stores, and monitoring, but not just the respiration rates, but volatiles and everything. So this is our dream, and I think we share it with James Hutton, and we share it with ADAS, and we share it with other research organisations around the UK. Okay, so I think I've talked enough about the reaction of fruit and vegetables now. I end with a slide that lists some of the other areas of research that we do at our centre down in Kent. We always welcome visitors. Of course, what I've been talking about was not just done by me, and in fact, most of it is not done by me, but my colleagues. Here are some of them. And it's probably not a complete list of the people that were involved in the work that I've shown, but there they are, smiling away. And I'll stop there and say thank you very much for listening to me, assuming you're all still there. Or not, as the case
Still
may
there.
be.
Thanks very much, Debbie. So if you're happy to take some questions, if anyone's got a question, let me get back so I can actually see if there's any hands going up. It struck me through that the big question would be, it's the old question. It's usually genetics by environment, but it's genetics times environment times management times storage now. Everything can potentially be much more complex. The smaller systems that you've got, will you think they'll start to allow us to look at genetic variation?
Yes, I do actually, because I think what's useful about having these systems is that we can increase the number of treatments that we use within trials, and therefore it allows us to do more direct comparison between different lines, varieties, etc. So yes, I do.
I mean, certainly if you're talking about the potato, if potatoes are going to shift to a different management system of growing, so reducing inputs, things like that, the behaviour in field will influence the behaviour in store. I mean, you see, is that commonplace in apples, for example? So a heavy, well, climate change. So things are changing. You're getting floods and
Yeah.
droughts, and so
Yeah.
how the fruit is formed under those conditions will be different, perhaps the year before. So your dynamic of your system has to be on its toes, as it were, to cope with that.
Yeah, so a couple of things that really affect how well an apple stores is the amount of dry matter that it has in it. So there is a move to increase the dry matter, in some cases by using, say, reflective mulches, which makes them store better. The density of the fruit, the porosity of the fruit makes a big difference. So if you think, and it would be the same with a potato, that in order to respire, and that is really important, they don't have lungs. So the only way that they can get the oxygen and CO2 in the right place is diffusion through the fruit. So if you have a year where you end up with fruit that is denser, then you're more likely, for example, to get the fruit going anaerobic at the center because the gas diffusion is harder. So there can be a massive difference from one year to the next. And the same could be with potatoes. So I think if you're starting to look at effects of potato irrigation, for example, it would really have an effect. One thing I think that we're noticing with the potato industry, so when I first started working on potato storage, whereas with apples, the industry was very aware that different apple varieties behaved in different ways. What the potato industry wanted then was one storage protocol that worked for all potatoes. I'm sorry, I'm talking to someone who knows much more about this than I do. It's quite scary talking about potatoes with James Hutton Institute there. But now the impression I'm getting is that there is much more of a realization that the different varieties behave differently, and therefore there's more of a thought about how to control storage. So it's not just that we're learning, but the industry's coming with us, that they will be influenced, and therefore we can do a lot more.
I think they moved away from the one ring to rule them all mentality.
Hopefully. Yes.
Anyone else got any more questions? I've still got some I can add. If there aren't any more, have you done anything about actually, instead of using it as a control mechanism to maintain quality, use it as a tool to manipulate quality? So you can shock nearly, say, for example, it's storing fine, but if you manipulate things slightly, you can play with sweetness.
I think there's huge potential there, actually, Derek. So with potatoes being able to reduce the sweetness, and to some extent the potato industry is trying to do that. We're also using this technology to look at the effectiveness of curing at the start of storage, which again we have, we have the capability of testing out different curing protocols, which is not something that you can do if you're working on a commercial potato store. It's way too big. You can't take risks. So we need to be able to have reliable research systems that we can play with, but also be confident that we are getting data which is relevant to the industry.
Agree. I mean, actually, to ally to that and to follow on, and for those that weren't there early, the Hutton through the Advanced Plant Growth Centre is building 6 4-ton crop storage systems, so much bigger than the Peapod ones, but ones that at times you may want to put Peapods in to match them because the industry, the large industries are conservative in their way forward. So there is sometimes the apple industry is fine. Potato seems to be a wee bit reluctant on Peapod, so we'd like to see comparability across scales just to make sure that works. But I think what we'd like to do going forward is trying to get an Internet of Things approach to a lot of these systems. So if we're all doing the same experiment, they're all interlinked. So we could see the data coming from the different systems at the same time. And that's kind of going back to what I was saying earlier about accruing. The more data you have, well, if you measure it, you can manage it. It's that old maxim. And if you can manage it, you can manipulate it. So I think the potential for changing nutrition of the crop, whatever it is in store, flavour, texture, what have you, I think is within our grasp if we can ally that to the genetics.
Exactly.
And I think the data is coming forward for all of these fronts going forward. So unless I can see, oh, is there a hand up at the top there? Did I see a hand there? No. Anyone got any questions before we close this? No, that's fine. Right. So Louise Sullivan has said, would you anticipate different responses in different tuber cultivars as you did with apples? And I think you kind of answered that.
The answer is yes. Yes, and we are seeing that. I mean, they are very different in their respiration rates, and their response to CO2.
So I'm curious about things like apples. I'm a lover of the red Macintosh Red, but they only seem to be coming from Canada at the moment into Aldi's. We don't seem to grow them anymore. But how long can people really store these things? I mean, what is the absolute limit?
Is there any point in storing longer than a year? Bramley apples can be stored easily for a year. And someone did once ask me this, so why don't we just store for 2 years? I said, well, why would you? A year is fine. And I think Gala stores very well. So I think Gala we can quite easily get to a year. Braeburn, another really popular UK variety, doesn't store so well. But we can get to 8-9 months. Unfortunately, some of the really nice varieties don't store well at all. So Cox is not a good storer. I guess we could probably go back now from what we know and get it longer. But it's unfortunately the really nice ones tend to be less good. But I think we can live with that. I don't know is the answer. Are we anticipating similar respiration between box and bulk?
I think that's going back to how effective is the smaller storage systems compared to the big one? Can you translate results up? So going back to your lab pod, how translatable is the data from that to a huge industrial store, for example?
Yeah. So I mean, I think basically we have to twin the development of the trials that we're doing in lab with more monitoring within stores to understand that. So interestingly, it appears that the airflow patterns give more consistency within a bulk store than they do in a box store. And I guess it's because you don't have so much possibility of shortcutting the airflows. So I think we can. I think we can ensure that we are simulating what's going on in the commercial stores, but I don't think that we should be complacent. I think it's really important to go and monitor what's going on in there. And I said we'd learned quite a lot. What we learned was how much, for example, the CO2 changes over time in potato stores, which the potato store managers were really quite surprised as to what was going on there. So what we want to do next is to put pods all over the place in the store. So we're waiting for possibility of doing that.
Sure. I seem to remember one of the big changes in potato storage was actually driven by, it was more by the engineers and the physicists, because they basically changed, instead of blowing, they changed the fan to suck. So you completely change the dynamic and flow. And actually the computing power now to model that allows you to more sensibly, you do your experiments in silico, so you're not wasting a big store. So that it's the advantage of science progresses, the ability to use more numbers and bigger numbers and model all those becomes evident. And I think it's going back to what I was saying earlier, the genomic side of things and the data you'll accrue, the detailed chemistry, whether it's looking at different types of volatiles as well, all of that I think adds to a better storage system going forward for the next generation.
Yep, exactly.
And of course, energy is really expensive now, so storage is expensive.
Yeah.
So, okay. If there are no more questions, we'd just like to thank Debbie. I'll be chatting to Debbie on a much more regular basis, and I'm sure you'll see her again. You show your usual appreciation. Well done. Thank you very much. And
thanks, Debbie.
Thank you.